Hello everyone, I hope you are doing well. Today we are going to do the lab of Ohm's law and Kirchhoff laws. Basically today we are going to measure voltages, resistors, as well as we are going to evaluate currents. It's using Ohm's law or using Kirchhoff laws. So let's start first with Ohm's law. So basically Ohm's law is saying that when you apply voltage on a certain resistance, okay, you get current. So any material has specific resistance R, and basically this R from Ohm's law, it says that it's equal to voltage over current. And basically we can see that the relationship of V, which is equal to R multiplied by I, and the resistance itself, it's constant for each resistance. It's a constant value usually, and basically this shows that when you increase the applied voltage, the current increases, and also if you decrease the voltage applied across the resistance, the current decreases. Okay, which basically we can draw it as if, for example, something like this. We have here the resistance, and we have here this one has a voltage of V, and this one is R, and the current going inside this circuit, it is I, and this is the relationship or the Ohm's law itself. Okay, so let's talk about Kirchhoff laws. Basically I will be using for this one, or this illustration, the circuit that we are going to use in this lab, which basically we have here a certain voltage, let's say V1, connected in series with a resistance I1. Then we have here another resistance I2 connected in series with a voltage power supply. Let's say this one is V2, and finally there's also here a resistance of R3, and it's connected to a voltage power supply of V3. And as we know, if we have a circuit like this, we should have a specific current moving in each line. Okay, so basically let's say that this one, it has I1. Let's say this one is going to have I2, and I'll assume the same direction, I3. So for Kirchhoff laws, let's talk about first the current law. Okay, well, Kirchhoff. Current law, and here basically it said that the summation of the current going inside a node, it's equal to the summation of the currents going outside of this node. So first we need to identify the node. So we have the node, let's say this is a node. Okay, currents going inside, which is I1 plus I2 going inside, and also I3 going inside, it's equal to the currents going outside. And as we have all of them going inside, basically, so the summation here is equal to 0. So this would be the first equation that we have. Okay, then we will be using the voltage Kirchhoff laws to evaluate the voltages. So here we have Kirchhoff voltage law, which basically tells us that the summation of voltages of voltages across closed loop is equal to 0. So this one, it's relying on the conservation of charge, and this one is relying on the conservation of energy. So basically here, let's assume that we have here two independent loops, this and this one and this one. So we will say that if the loop going this way, okay, so this voltage has a positive mark here, negative here. The current is going in this direction inside the resistance, so we'll have here these polarities, plus and negative. We define basically the polarities of each element. So this one is positive, this is negative. This one is positive and negative because the current is going here. This is negative and positive. And basically the current is going like this way, so it's positive and negative. Okay? Then basically we need to find the voltages inside this loop and sum all of them. So let's get the first sign that we see when we move around. So we see here negative V1. So let's say negative V1. It's positive I1, which basically the voltage on this resistance is equal to I1 multiplied by I1. Okay, so going here, it's going to be plus I1. Then we go here, we find a negative, we see the first sign is negative, so a negative I2, which basically the voltage on resistance 2. And this is going to be a negative I2, and we see positive V2 plus V2. So we have here, and all of this is equal to 0. So this is going to be our second equation, second one. Then we will do the third equation, which basically is similar. Let's use this one, this closed loop. So we see here, we go from here, we start from here and go up. We see minus V2. We have minus V2. Then here we see plus I2, which basically the voltage on R2, resistance, the second resistance. So basically plus R2, Then we go in the loop here. So we see it is negative I3, then plus V3. And this is basically the second or the third equation. So we have three equations with three unknowns. We know the voltages, we know the resistors, and basically we don't know the currents. So using these three equations, we can solve them in order to find what is the value of the current, the first current moving in this direction, and this one and this one. When you do this, you will find that one of them, or maybe two of them, is going to be negative, which means the direction is opposite of this current. So this is basically a summary of the circuit used in this lab and how to evaluate the currents itself. Also, you can, instead of using these equations to do the measurements of the currents, you can basically do the measurement using the digital multimeter. And basically, if you have here, let's say we have a digital multimeter and we are measuring the voltage, so we can basically put the probes in parallel to this resistance, and we can find basically the voltage on the third resistance. And we know, when we know this voltage on the R3, and we also know the value of R3 from these two, we can use or the Ohm's law, which basically tells us that I3 is equal to VR3 over R3. So using digital multimeter, we can evaluate the value of the current in each one. So basically, we would like to compare the measured currents with the evaluated currents. I hope this is clear to you. So the resistors that we are going to use today, it's basically ceramic resistance, okay? And we are going to use 3 of them, which different 3. And we will be using the white breadboard to do the setup. And I'm going to illustrate right now how to use the white breadboard. So to use the white breadboard, there are different types. So we are talking about this type right now, which basically this type, it shows us many holes. It's kind of something that has, or a board that has many holes. And let's, for example, draw it. Here, this is the white breadboard, and it basically it has different groups. So we have here, you can have here a gap or a groove. Then you have here a section, another section. You have the section here. Okay. Then you will find there is a red line which says positive, and a blue line which says negative. Same here. So basically, we will find many holes here, and so on. And we are going to have here also some holes. These holes basically is made to insert the component, the electrical component, like the resistance, inside. Okay, so we'll put it inside, and all these holes are connected from inside. So basically, all of them are one node. This side's all of it is one node. This line is also all of it one node. So all of them, all these holes are like these points are connected to one another, and all of these are connected to one another. Then we will find in the middle kind of 5 holes for each one, some rows, and we will have at each row there's 5 holes. Then you will find another row. Each 5, they are one node. Each 5, they are connected to one another. So each one is one node. One node. So this is one node. These are one node. This one node. This is one node. And so on. And we go in this direction. So basically each 5 are the same connection. So if you have this wire, for example, and this wire that comes from this connection and this connection, this one is going to go in one hole, and of the 5 holes, let's say, for example, if we have 5. So we connect this one, and basically all of them are connected internally inside the white breadboard. I have, it was clear, and also that each of these 5s are one node, just one node. Okay, and it's easy, it's facilitated for us to put the pins in each one of them. Okay, hopefully it's clear to you how to do this one.